So a few more remarks on thermodynamics, and that will bring us to a point where we could get into serious problem solving, all that we require for this level. Now, in my previous session, the first session on thermodynamics, I mentioned about some basic elementary processes, how to calculate the heat transfer, work done, change in internal energy on various processes. Now, we looked at two thermal properties in the last class. One was Cp, the other one was Cv, right? That was related to the gas, right? There is a property that I'm going to introduce which would not be about the gas, it's going to be about the process. It will also be in a certain sense about the gas, but then primarily it will be about the process. So if there is a certain process, and for that process, say there is heat delta Q, which is required to carry that process out. Amount of heat delta Q is required to carry that process out. And say, for n moles, it brings about a change in temperature delta T. A certain process involves delta Q joules of heat. To raise the temperature of n moles in that process by an amount delta T. To raise the temperature by an amount delta T for n moles during the process. We then define what's called the molar specific heat for the process. C for the process. It's defined as the amount of heat delta Q required during the process to raise the temperature of 1 mole by an amount delta T, by a unit amount. This is what? This is the amount of heat required to, this entire expression represents the amount of heat required to raise the temperature of 1 mole by a unit degree. Yes or no? Right? This entity is called C, the molar specific heat for the process. Molar specific heat for the process. Right? Now, for some of the elementary processes that we have looked at, for example, an isothermal process. For an isothermal process, delta Q is non-zero, but delta T is 0. For an isothermal process, delta T is 0. So if delta T is 0, then the C for an isothermal process is infinity. C for an isothermal process is infinity. Right? For an adiabatic process, delta Q is 0, C equal to 0. Yes or no? For an adiabatic process. For a constant volume process, for an isochoric process, C is the same as Cv. Because for an isochoric process, the amount of heat required to raise the temperature of 1 mole through a unit degree is the same as Cv. Right? So C for an isochoric process is Cv. For an isobaric process, Cp. Right? Now, so this is this is related of course to the process and also related to the gas, because the amount of heat required for the same kind of process for different gases in general could be different, right? But then it has the stench of the process as well, where Cp and Cv are not about the process, those are about the gas. Those are about the gas, right? Fundamental properties of the gas. Now, let me introduce to you yet another process, which is of the form PV to the power n equal to constant. Everything for an ideal gas by default, PV to the power n is constant, where n, if it is gamma, then it's an adiabatic process, right? But when n is not gamma, then PV to the power n equal to constant is referred to as a polytropic process. It's called a polytropic process. Polytropic process. N is called the polytropic exponent. N is called the polytropic exponent. Gamma was the adiabatic exponent, N is the polytropic exponent, right? Not within the jurisdiction of things that we are supposed to know right now, how this process could be produced. But then, by some mechanical means, let's say a process of the kind where pressure and volume vary as per PV to power n equal to constant would be deemed a polytropic process, right? Now, if there is a polytropic process, then, well, calculation of work done would be integral P dV, V changes from V1 to V2. Change in internal energy would be NCV delta T, right? So, let's say in a polytropic process, the work done is going to be integral P dV when V changes from V1 to V2. When V changes from V1 to V2, that's the work done in any process. Now we'll carry this integration out for a polytropic process in which initial pressure is P1, initial volume is V1, final pressure is P2, final volume is V2, and the changes are commensurate with PV to power n equal to constant. PV to power n equal to constant, right? Now, let's say this constant is C. Let's say this constant is C. What I could then do is I could replace P by C into V to power minus n, P as C into V to power minus n. V runs from V1 to V2. Right? Which then, this C can wriggle out of the integral sign, and it's going to give me V to power 1 minus n divided by 1 minus n. V runs from V1 to V2. Right? Now when I integrate this, it turns out to be C into V2 to power 1 minus n minus C into V1 to power 1 minus n divided by 1 minus n. Right? Now, for the process, the pressure and volume will always be subject to this condition. P1 V1 to power n is P2 V2 to power n. Each will be equal to C. So what I could do is, this C here, I can write as P2 V2 to power n. This C here, I write as P2 V2 to power n. So if this C is replaced by P2 V2 to power n, whereas this C is replaced by P1 V1 to power n, then what I end up getting is, this is P2 V2 minus P1 V1 divided by 1 minus n, isn't it? This will become P2 V2 minus P1 V1 by 1 minus n, yes or no? Does it make sense? Now, for an ideal gas, P1, V1, let's say the initial temperature is T1, would be nRT1, right? P2, V2, if the final temperature is T2, is going to be nRT2, right? So this P2, V2 I can write as nRT2 minus nRT1, yes or no? And in the sense, you know, let me call this n naught, number of moles, because this n is not the number of moles, this n is the polytropic exponent. So let me call the number of moles as n naught. So this would become like a n naught R T2 minus T1 divided by 1 minus n. This n is not number of moles, this n is the polytropic exponent. This n naught is number of moles of the gas involved in the process, right? Now, for a polytropic process, then I am seeking to calculate the molar specific heat for the process, right? I want to calculate for a process PV to power n the molar specific heat C for the process. But before that, we already have the expression for work done in a polytropic process in which temperature changes from T1 to T2 for n naught moles of the gas. That turns out to be n naught R delta T. T2 minus T1 is delta T. T2 minus T1 is delta T, the change in temperature final minus initial, divided by 1 minus n. The change in internal energy, no matter what the process is going to be always NCV into delta T. N is n naught in this case. So n naught CV into delta T, right? Now, if C is the molar specific heat for the process, if C is the molar specific heat for the process, then the heat required during the process must be n naught C into delta T, where C is a property for the process, right? The amount of heat required for 1 mole for a unit degree would be C. So for n naught moles and for change in temperature delta T, this is going to be the heat required, right? Now all that we need to do is to perform the last rites on this, carry out the first law of thermodynamics, right? So when I deploy the first law of thermodynamics to this, then heat supplied must be work done plus change in internal energy, right? So n naught C delta T, that's the heat supplied, is work done, which is this n naught R delta T divided by 1 minus n plus delta U, which is n naught C delta T CV delta T, n naught CV delta T. That's a change in internal energy, right? So that gives us C, the molar specific heat for the process, as R by 1 minus n, which is process dependent entity. N is a property of the process, the polytropic exponent, plus CV, which is the process of the, which is a property of the gas, which is a property of the substance involved in the process, right? So this could also be written as R by 1 minus n, and CV is R by gamma minus 1. CV is R by gamma minus 1. And very clearly, if n is gamma, this will become 0. When n is gamma, this is going to become 0, isn't it? If n is gamma, this is going to become 0. That means when the polytropic process becomes adiabatic, that happens for n equal to gamma, C for the process becomes 0 as is expected, isn't it? C for an adiabatic process must be 0. Right? So that's a boundary check that we could perform with this. So this is important for a polytropic process. Therefore, for polytropic process PV to power n equal to constant, this constant, this is this C, by the way, don't mix up this C with that constant. You know, so many variables coming with different views. This C is not that constant C. This is not this C, by the way. This C is molar specific heat at this is the molar specific heat for the process. This is only the constant for the process. So don't mix it up. And that turns out to be R by 1 minus 1 plus R by gamma. So C for the process, molar specific heat for the process is R by 1 minus n plus CV. CV is R by gamma minus 1. This is the gas dependent entity. This is the process dependent entity. Right? So this is how you obtain the molar specific heat for the process. Suppose there is a someone carried out a process of the following kind. Say there was a monoatomic gas. Say there was a monoatomic gas going through a process which is PV to power minus 1 equal to constant. Going through a process PV to power minus 1 equal to constant. Right? And say there were n moles of the gas. And they said, find the amount of heat required to raise the temperature of the gas during the process by an amount delta T. They said find the amount of heat required during the process for n moles by an amount delta T, to raise the temperature by an amount delta T. What you do is find the molar specific heat for the process. Find the molar specific heat for the process. What is that? R by 1 minus n. N in this case is minus 1. The polytropic exponent here is minus 1. So R by 1 minus 1 means R by 2. Right? Yes or no? For a monoatomic gas, this is CV, which is 3R by 2. CV, this is CV, which is, see, gamma is 5 by 3. So this will become 3R by 2. The CV for, so 3R by 2. That makes it 2R. Yes or no? Huh? Gamma for a monoatomic is 5 by 3. So this will become 3R by 2. CV for this R by gamma minus 1 is actually CV. CV for a monoatomic gas is 3R by 2. Right? So once you have the molar specific heat for the process, then life becomes very simple, because then the amount of heat required for n moles is going to be n into C, which is 2R into delta T. That's going to be the heat required. If delta T is 50 Kelvin, then and n is 1 mole, then that's going to be 100 R joules, 100 R joules. Right? That's the heat required. So computation of the C for a polytropic process is R by 1 minus n plus R by gamma minus 1 is important to know and remember. Right? You must remember this result for a polytropic process with polytropic exponent being n. Right? Yes, you have a question? No. Now, see, sometimes they may give you something like this. They may say there is a process like P squared V is constant, and you want to find C for the process. What would you do? Take the square root of this. This would become PV to power half equal to constant. If you took the square root of this will become PV to the power half is constant. Then what's the polytropic exponent? Half. So what's the C for the process? R by 1 minus half plus the CV for the gas. That's going to be the molar specific heat for the process. Right? Yes or no? Suppose they give you PT equal to constant. There is a process in which pressure into temperature remains constant. Right. What you do is, see, in the polytropic exponent, in the polytropic process, the polytropic exponent is obtained by connecting pressure and volume. So eliminate temperature. So T could be written as PV by NR. N is N naught, number of moles of the gas, equal to constant. So that makes it P squared V is constant, which reduces to this, which will reduce to this, taking the square root, isn't it? This is like P squared V is constant because N naught and R are constant, and that will readily give you the polytropic exponent N as half, and then you have the molar specific heat of the process available as R by 1 minus N plus CV of the gas. Clear? Now, these processes are essentially elements of what is called a cycle. We are not interested in the processes alone. We are interested in a collection of processes. A thermodynamic system revolves around a collection of processes. These processes occur one after the other, bringing the gas back to the same state, same thermodynamic state, again and again, time and again. This is what happens. Say, for example, a collection of processes could be like this. A gas goes from state 1 to state 2 along some process, right? Then it goes from 2 to 3 along some other process, and then it goes from 3 to 4 along some other process, and then comes back to 1 along some process, right? So this, for example, a collection of 4 processes bringing you back to state 1. Collection of processes, the processes are 1 2, 2 3, 3 4, 4 1. Right? Now, collection of all these processes, let's say bringing you back to the same state, is called a thermodynamic cycle. That's a thermodynamic cycle, right? Now, see, again, the objective of a thermodynamic cycle is mechanical work output, Some of these processes are hungry for energy. They would take energy or heat from the surroundings. Some of these processes would reject heat to the surroundings. Whenever there is heat absorbed by the thermodynamic system, then that delta Q is algebraically positive. When rejected, then that delta Q is negative, right? So let's say in this, heat is delta Q1 involved. In this process, let's say delta Q2, that's a heat rejected. That means delta Q2 would be a negative number. Say this, is heat rejected, delta Q3, and say this is heat absorbed, delta Q4. Okay, you could have done the other way around also, and the entire that's only a convention. It's just to distinguish between heat absorbed and heat rejected, so that positive sign would mean that it's heat absorbed. Or you could have taken the other way around. In chemistry they do that only, isn't it? So you don't know your chemistry, right? In chemistry, thermodynamics is all ulta pulta. Okay, so thermodynamics should not be stressed upon in chemistry classes, because that's all wrong. Not wrong really, but that's not the way thermodynamics is. In any case, all that I intend telling you is why. What was your question? Why absorb positive? Just a convention. I could have taken all absorbed negative and all rejected positive also, right? Now, when you are executing this cycle 1, 2, 3, 4, 1, right? This cycle is 1, 2, 3, 4, 1. When you are executing this cycle 1, 2, 3, 4, 1, then coming back to 1, you are coming back to the same temperature state. That means in a full cycle 1, 2, 3, 4, 1, when you are arriving at the same state again and again, then upon arrival at the same state, during the cycle, then the net change in internal energy during the cycle must be 0, right? So delta U for the cycle must be 0, right? For a full cycle, delta U for the cycle must be 0. Now, since delta U is 0 in a full cycle, the heat supplied, the net heat supplied in a cycle must be the net work done by the cycle. The net work output of the cycle will be the net work output of the cycle, because change in internal energy is 0 during a full cycle, right? So all the heat that is supplied to a cycle for a full cycle is completely consumed in doing mechanical work for the cycle, right? Now, therefore the work done during a cycle would be delta Q1 plus delta Q2 plus delta Q3 plus delta Q4, which is the net delta Q for the cycle. What's net delta Q for the cycle? The algebraic sum of delta Q1, delta Q2, delta Q3, delta Q4? Yes or no? This could be 20 joules, this could be minus 1 joule, this could be minus 2 joules, and this could be 14 joules. Then the net delta Q supplied to the cycle is going to be what? The algebraic sum of these delta Qs, right? So the net delta Q associated with the cycle would be delta Q1, algebraic sum of these delta Qs. The algebraic sum of these delta Qs, some of them positive, the others negative, would give me the net delta Q associated with the cycle, the algebraic sum of all the delta Qs in various processes that involve the cycle, right? This is going to be also equal to the net mechanical work output of the cycle. This is also equal to the net mechanical work output of the cycle. Clear? If you add all the delta Qs algebraically, keeping the sign convention intact, positive when absorbed, negative when rejected, that's going to give you the net heat assimilated by the cycle, right? And that in turn is going to be the work output of the cycle. That's going to be the mechanical work output of the cycle. And if this work output takes place in delta T seconds, if a full cycle is executed, see this figure, this indicator diagram doesn't tell you the time it takes to execute a full cycle, isn't it? This does not tell you the time it takes to execute a full cycle, but then there is a certain time that it takes to execute all these processes once, right? And in that time, this would be the work output of the cycle. You divide this work output by the time, you get the power associated with the cycle in watts, right? Now, the cycle has a certain efficiency. This is the output of the cycle. The efficiency of the cycle is obtained by the ratio output to input. That means, in order to produce this output, what has the cycle consumed? What has the cycle consumed. That would be the input to the cycle, right? This is delta W for the cycle, and this is also equal to the output of the cycle. This is also equal to the output of the cycle, right? This is the mechanical output of the cycle, right? Now, in order to... Yeah, but then we don't run that cycle. We don't run a cycle in which, you know, it's consuming energy. If we are running a thermodynamic cycle, it's with a view to get a work output from the cycle, right? And if it turns out to be negative, will not mean that that will still be the input. Input to the cycle will mean something else. Input to the cycle would really be all those processes in which heat is actually supplied to the cycle. The cycle has consumed energy in certain processes, right? It has taken energy, but when it has rejected energy, it has done it out of spontaneity. When it has been supplied with heat, that has not happened out of spontaneity. We have actually supplied that amount of heat in various processes that involve the cycle, right? So, input is actually only those delta Qs that are positive. To execute the cycle, whenever heat is rejected, it's rejected because of the thermodynamic nature of the processes. But when heat is absorbed, that's a heat I'm supplying to execute a process. Right? We are not spending money to reject heat, but we are spending money to supply heat. Right? So wherever we have supplied heat, that's the expense to run the cycle. That's the expense to run the cycle, which is the input of the cycle. So in this case, for example, to run the cycle, the amount of external involvement in terms of heat coming from outside is going to be delta Q1 plus delta Q4 are entities that are supplied to the cycle. Yes or no? So the input to the cycle in this case is sum of all the positive delta Qs. Input to the cycle is sum of all the positive delta Qs. In this case, that's delta Q1 plus delta Q4. That's the input to the cycle. And the algebraic sum of all the delta Qs, that's going to be the output of the cycle. Whereas sum of only the positive delta Qs will be the input to the cycle. That's the expense to run the cycle. That's the expense to run the cycle. That's the cost of running the cycle. The sum of the positive delta Qs.
But if volume is decreasing, like from 4 to 1, the volume decreases. So value should be negative.
No. Don't think. No. So what? Change in internal energy could be positive, far exceeding the negative work done. Then their sum could be positive, isn't it? Work done is negative will not mean delta Q would be negative. Because to calculate delta Q, I would have to add the change in internal energy also, right? In this case, do you realize that it's possible that the temperature is increasing? Change in internal energy is positive, far more than the negative work done. And then the heat would be required by the cycle, by the process, isn't it? And then the efficiency of the cycle, is going to be output divided by input. And percentage efficiency is going to be into 100 will give you the percentage efficiency of this is fractional efficiency of the cycle. Eta into 100 will give you the percentage efficiency of the thermodynamic cycle. Yes.
Again, why isn't only the heat expelled out of the system or the cycle equal to the work output?
No. Because of the first law of thermodynamics. The net delta Q by the cycle is what? Change in internal energy in a cycle plus the work done. Right? That's first law of thermodynamics. So see, delta U is 0. This is net delta Q supplied to the net delta Q supplied to the cycle is the work done because this is 0. This is the net delta Q. That means algebraic sum of the delta Qs that are involved in the cycle, isn't it? This delta Q is delta Q in 1, 2 plus delta Q in 2, 3 plus delta Q in 3, 4 plus delta Q in 4, 1. That's a total delta Q involved with the cycle. Positive as well as negative. Clear? So far so good, right? So essentially, this delta Q2 and delta Q3 that you see are like emissions coming out of the car exhaust, carrying humongous amount of energy with them. sometimes going unutilized, most of the times going unutilized. In fact, the efficiency of a standalone cycle is this, right? This is how we calculate the efficiency of a standalone cycle. But in very sophisticated applications, what they do is part of the energy which is expelled, delta Q2 and delta Q3, is recycled back to the system, in the sense, you know, the emissions could be carrying away delta Q2 and delta Q3 amount of heat expelled. Either it could just be released and let go, or part of this heat could be rechanneled back into the cycle as delta Q1 and delta Q4, which means the input requirement will decrease and therefore the efficiency will increase. But it's not always done, because sometimes to channelize the expelled heat back into the system is by itself a cost, You know, there are gases coming out, expelled out of the system, for example, or heat coming out of the system. Then to translate that heat back to the system would be a challenge, because it will involve, say, very expensive heat transfer equipment. That's a cost to the system. It will add bulk to the system. There will be a cost involved with the system, and therefore it does not get reasonably justified, right? But in very sophisticated applications where we have to be austere about the energy that is being consumed by the cycle, and it could be a space application kind of a thing, then we would have to be very conscious about the heat that is being rejected out. We would have to focus on how we could get back this into the system. Sometimes certain systems run based on multiple cycles, which means the heat rejected by this cycle could be an input to another cycle. So then the compounded efficiency will increase. Right? Now, a very common cycle is an Otto cycle. Otto is not AUTO wala Otto. Otto was the scientist who invented this cycle, right? And it consists of the following processes. The indicator diagram for this cycle is as follows. We have, let's say, a gas going from state 1 to state 2 adiabatically. 1, 2 is an adiabatic process. Then 2, 3 is an isochoric process. Three, 4 again is an adiabatic process. And 4, 1 is an isochoric process. One, 2, 3, 4, 1, that's the Otto cycle. That's an Otto cycle. Say, temperature of point 1 is T1, of point 2 is T2, of this point 3 the temperature is T3, and T4 of this point, right? Now, V1 equals V4, volume of 1 and volume of 4, they are equal, right? Volume 2 equals volume 3, right? And like I mentioned in the last class, PV to power gamma is constant for an adiabatic process, right? For 1 mole of the gas, I can write P as RT by V into V to power gamma equal to constant for an adiabatic process. Or we end up getting TV to power gamma minus 1 equal to constant for an adiabatic process. TV to power gamma minus 1 is constant for an adiabatic process. Clear? Now, let's aim at computing the efficiency of this Otto cycle 1, 2, 3, 4, 1. Let's look at the process 1, 2. What kind of a process is it? Adiabatic process. What's the heat supplied to the system during an adiabatic process? 0. So delta Q during 1, 2 is 0. Yes or no?
Yes.
Right? 2, 3. Constant volume process. Heat supplied is change in internal energy, isn't it? Because in an isochoric process, work done is 0. Work done is 0 in an isochoric process, right? And heat supplied, therefore, must be change in internal energy. Work done in this process is 0. So heat supplied must be change in internal energy. Heat supplied must be change in internal energy. Yes or no? And change in internal energy in 2, 3. Let's say, let me take it for 1 mole, because the efficiency will not matter whether I do it for 1 moles or 2 moles or 100 moles. So for 1 mole, the change in internal energy is going to be CV into T3 minus T2. Final temperature minus initial temperature. Now, realize that when I go from 2 to 3, see, look at this, PV equal to constant. PV equal to nRT, sorry. PV equal to nRT. Now, when V is constant and pressure decreases, temperature will decrease, isn't it? At constant volume, if you decrease the pressure, the temperature will decrease. Yes or no? At constant volume, if you decrease the pressure, pressure is decreasing, so temperature will decrease. So T3 will be less than T2. Yes or no? T3 therefore will be less than T2. Yes or no? Right? And therefore, this will be a negative number. That means, yes, in 2, 3, heat must be rejected from the system. This is a negative number because T3 is less than T2. So heat must have been rejected during this process. Clear? What is delta Q in 3, 4? 0. Why? Because it's an adiabatic process. Adiabatic process. Right? Now, what about the process 4, 1? Delta W 0. Why? Isochoric process, no volume change, no volume change, right? Work done is 0. And the heat therefore that is supplied in 4-1 must be entirely change in internal energy, which must be NCV or 1 mole, let's say, CV into T1 minus T4. Hey, at constant volume, you are increasing the pressure, so the temperature is increasing. So T1 must be more than T4. T1 turns out to be more than T4. And therefore, this is a positive number. So heat is absorbed during this process. Heat is absorbed during the process. This is the positive heat. That's the negative heat. Their algebraic sum would be the net work output of the cycle. The net work output of the cycle would be the algebraic sum of these. Yes or no? Yes, sir. Right. So the work output of the cycle would be the algebraic sum of these delta Qs, right? The delta Q for the cycle is the work output of the cycle, which is this CV into T3 minus T2 plus CV into T1 minus T4. This is positive, this is negative, this is their algebraic sum. That gives me the work output of the cycle, the mechanical work output of the cycle, right? The input of the cycle would be the positive delta Q, or the sum of all the positive delta Qs. What's the only positive delta Q here? Delta Q 41, right? That's going to be CV into T1 minus T4. And this is the output of the cycle. Now if I divide output by input, I get the efficiency of the cycle. If I divide output by input, I get the efficiency of the cycle. Eta of the cycle is output divided by input right, which is 1 plus T3 minus T2 divided by T1 minus T4. Yes or no? This could have been written as 1 minus T2 minus T3 divided by T1 minus T4, right? I could have then written this as 1 minus T2 by T1 into 1 minus T3 by T2 divided by 1 minus T4 by T1. Taking T2 common from the numerator and T1 common from the denominator. This is what I get. Yes or no? Right now? Now, see, I apply the adiabatic law between 1 and 2. T1 V1 to power gamma minus 1 is T2 V2 to power gamma minus 1. Yes or no? Right? So T1 V1 to power gamma minus 1 is T2 V2 to power gamma minus 1. That's for the adiabatic process 1, 2. Right? Similarly, T3 V3 to power gamma minus 1, T3 V3 to power gamma minus 1 is T4 V4 to power gamma minus 1. Right? Now when I divide this by this, V1 is the same as V4 and V2 is the same as V3. They will get cancelled when I divide. So on dividing these two equations, I end up getting T1 by T4 is T2 by T3. Or T3 by T2 is the same as T4 by T1. T3 by T2, T3 by T2 is the same as T4 by T1. And if T3 by T2 is the same as T4 by T1, this will get cancelled. 1 minus this. So this turns out to be 1 minus T2 by T1. 1 minus T2 by T1. That's the efficiency of the Otto cycle.
Yes, sir.
Do you all understand this? Huh? Let me also tell you that in the event you have a mixture of gases, right? Let's say a gas, N1 moles of a gas with CV equal to CV1, N2 moles of a gas with CV equal to CV2, and so on and so forth, right? a number of gases, say nk moles of a gas with Cv equal to Cvk. This is a mixture of gases, these being their Cvs and these being the number of moles of the gas, right? The Cv of the mixture, is given by the the weighted mean of these Cvs, n1 Cv1 plus n2 Cv2 nk Cvk divided by n1 plus n2 plus nk. Why? Why is the Cv equal to the weighted average of these Cvs? Huh? Energy. What? So no, the point is simple. The entire mixture means, you know, all gases now would be at the same temperature T, right? No, not even close to that. No relationship with this, with the business of center of mass when it comes to this. No, please. The total internal energy of the system is going to be what? N1 Cv1 into T plus N2 Cv2 into T plus Nk Cvk into T would be the total internal energy of the system, right? Now suppose the equivalent Cv is Cv. Suppose the equivalent Cv is Cv, and now for how many moles of this gas? The total internal energy Nk, and at a temperature T. That means instead of having a mixture of gases, you could have had the same moles of the gas at the same temperature with the property Cv equal to Cv. The total internal energy would be the same. That's when the Cv would be the equivalent Cv. Isn't it? Did I not tell you that the internal energy is going to be NCV into temperature? That's a change in internal energy. But the absolute internal energy, F by N into F by 2 RT, and F by 2 into R is Cv. So NCV into T is the absolute internal energy at absolute temperature T, right? So then Cv is the weighted average of these. Can you see that? Cv then is the weighted average of the Cvs. Similarly, you might want to ponder on why Cp of the mixture is also the weighted average. That's not going to be difficult to, yes. You didn't understand this. Okay. See, this gas, say, this mixture is equivalent to a single gas, to some gas, equivalent gas. And how many moles of the gas? N1 plus N2 plus Nk. Same mass, right? Same number of moles of the gas at the same temperature T and having a property Cv. These two are equivalent. Now, the internal energy of this must be the same as internal energy of this. What's the internal energy of this? Number of moles into Cv into T, and that must be equal to the internal energy of this, which is N1 Cv1 into T plus N2 Cv2 into T plus Nk Cvk into T. Equate their internal energies. You get the equivalent Cv for the mixture. Right now? No? What? Similarly, Cp for the mixture is going to be the weighted average of their Cps. N1 Cp1 plus N2 Cp2 plus Nk Cpk divided by N1 plus N2 plus. Purohit, did you understand this? Sure, na? Why this then? वहां पे तो internal energy I said. Cp minus Cv is R. Not multiply, We write all these CV1s as R minus CP1, R minus CP2, R minus, this will be written as R minus CP of the mixture. Yes. See, all these CVs can be written as R minus CP1, R minus CP2, R minus CPK, and this CV can be written as R minus CP of the mixture. When you divide, the CP of the mixture will turn out to be this. Yes or no? No? The gamma for the mixture is going to be this, divided by this is going to be the gamma for the mixture. The adiabatic exponent for the mixture is going to be Cp of the mixture divided by Cv of the mixture. Yes or no? Sounds all right?